Welcome back to chapter 3. Before I proceed, shout out to Dr. Ingrid Yap, who patiently follows and views all the videos I post. Shout out to Dr. Chiqui Suarez as well as Dr. Therese Bustos from the University of the Philippines College of Education. Okay, let's recall that in 3.8a, we discussed the properties of inequality and the ways of writing your solution set, which you already have had in your previous years. For this lesson, the objective will be to apply two theorems to solve a quadratic inequality. Let's start by defining a quadratic inequality as this statement here, where A, B, C element real and A not equal to 0 represents a quadratic inequality which can be written as either ax squared plus bx plus c greater than 0 or ax squared plus bx plus c less than 0. At this point, we are familiar with the solution of this statement, ax squared plus bx plus c equals 0, here where a, b, c element real and a is not equal to 0. This is our familiar quadratic equation in standard form, where the solution is given by this quadratic formula . This is the solution to this equation, meaning that these values here, negative b plus or minus square root of b squared minus 4ac over 2a, will satisfy this equation. If you substitute these values here one at a time for x, then the left hand side becomes 0. Remember, we had our roots are either real and equal, or roots are real and equal, and the roots are imaginary. We can only visualize the solution to this equation on the number line if the roots are real. Okay? So if this is the number line, I can have these roots graphed on the number line. For example, this one and this one will represent my root. Negative b minus the square root of b squared minus 4ac all over 2a, and here I get here negative b plus square root of b squared minus 4ac all over 2a. Okay, this is the case where the roots of this quadratic equation are real and not equal. So we can graph these ones here. So these are the numbers that will make this left hand side equal to 0. Our objective for this lesson will be to find out what will be the numbers that will make this expression be greater than 0 or this expression be less than 0. Clearly, I am demonstrating the roots of this equation as real and unequal. Our interest now is to find the values of x that will satisfy this inequality or this inequality. if I ask you to find those solution sets, we are considering looking at three regions where these roots here have divided the number line. First, this is region 1. Second, we have here region 2. And third, we have region 3. Which means, I expect that the solution to this inequality can either be in this region here, or this region, or that region. Also, the solution to that inequality can either also be here, or in that region. Okay? Let's have a particular example. For convenience again, I'll be using this equation here. X squared minus 5x minus 6 equals 0. And I want to find out the solution set to this equation. I will do that by factoring. X minus 6, x plus 1 equals 0. And from the zero product property, I have either x equals 6 or x equals negative 1. Now, these are real and unequal roots, so I can graph them on the number line. Negative 1, let's say this is 0, negative 1 will be here, and 6 is approximately there. And these are my solution. These are elements of my solution set. So, negative 1 or 6. These are the only two real numbers that will make the left-hand side of this equation be 0. That's why we call them the solution set. Okay, now, suppose I want us to consider x squared minus 5x minus 6 greater than 0. And here, I want to consider x squared minus 5x minus 6 less than 0. By the sense of saying that the inequality x squared minus 5x minus 6 can be either this one or this one, when we find the solution set of this one here, then we already know the solution set of this. Because whatever is not here should be there. Okay? Let's try again to recall what I said in the previous slide, that this region 1 here may be a solution region. This is region 2 here, and then this is region 3 there. Maybe also solution regions for either these inequalities. Okay, what am I trying to drive at here? Suppose I will get a value of x less than negative 1. Let's say here x is negative 2. And I will try to substitute it here. So when x equals negative 2, I will get here negative 2 squared minus 5 times minus 2 minus 6 is greater than 0. And let's try to find out what this one gives us. This is 4 plus 10 minus 6 is greater than 0. 10 plus 4 is 14 minus 6 is 8. It is indeed true that 8 is greater than 0. My conclusion here is it will be all x to the left of negative 1. So I am now saying that one of my solutions now is from negative infinity up to negative 1. This may not be all. Okay, so for example, I get another x in this region. Let's say x equals 0. And then substitute it here. So I get here 0 minus 0 minus 6. Is minus 6 greater than 0? The answer is clearly no. So, which means this region where 0 belongs is not a solution to this inequality. If it is not a solution to this inequality, then it must be a solution to this inequality. So I'm now saying that initially, my solution to this inequality will be this region, or that is negative 1 up to 6. Remember, I cannot write that as minus 1 and 6. This one doesn't make sense because this one describes a segment from negative 1 up to 6. In other words, all these points here will satisfy this inequality. Now, we have left out region 3. Suppose we want to get a number greater than 6. Let's say x equals 10. We may either test x equals 10 in this inequality or in this inequality. Let's say I will test x equals 10 here and find out who owns this region of solution. So when x equals 10, I will have here 10 squared minus 5 times 10 minus 6. Is this less than 0? This is 100 minus 50 minus 6. Clearly, this is not less than 0. 100 minus 50 is 50. 50 minus 6 is 44. 44 is not less than 0. Which means this interval is not a solution to this inequality. So I will have this interval go to this solution of this inequality. Therefore, the solution of this inequality will now be this interval union the interval where 10 belongs. So this is 6 up to positive infinity. We have covered all the regions. And notice that these regions of solution have been split into either the inequality is greater than 0 or less than 0. What we did here is we did a brute force way of showing where the solution of this inequality lies or this inequality. Let's take now these two theorems that we have been saying and find out how we can solve these two inequalities using the theorem. Again, let's consider this inequality, ax squared plus bx plus c not equal to 0. And we are solving two of them according to the trichotomy law. We get here ax squared plus bx plus c greater than 0 or ax squared plus bx plus c less than 0. This is always an assumption here. ABC element real, a not equal to 0. We are solving a greater than inequality. Here we are solving a less than inequality. Okay, by the aid of the two theorems we have been saying, suppose this left-hand side of this inequality is expressed as a product of two factors, p and q. Then we are saying this theorem, if the product p times q is greater than 0, then case 1 will give me p greater than 0 and q greater than 0, or case 2 p less than 0 and q less than 0. And the solution set will be case 1 union case 2. What is this theorem trying to tell us? If we are solving a quadratic inequality which is greater than 0, both the factors should have the same signs for the cases. So either both are positive or both are negative for us to have a positive product. Remember, when we are solving an inequality, we are bound to note what we are trying to solve at. Are we solving a greater than inequality or are we solving a less than inequality? If your inequality is greater than, then this theorem will give you the possibilities of the behavior of P and Q. The first case is both are positive and the second case is both of them are negative. Again, I will say, solving a greater than inequality, both of the factors should have the same signs. Here both are positive, here both are negative. In both cases, you will get a positive product. Okay, what about if we solve this inequality? Then, the theorem that we consider here will be if P times Q is less than 0, then case 1 here will be that P greater than 0 and Q less than 0. Or case 2, P less than 0 and Q greater than 0. And your solution will be case 1 union case 2. What this theorem is trying to tell us is that if you're solving a less than inequality and we have these two factors whose product is less than 0, then the factors should be written such that they have different signs. So one is positive, one is negative, one is negative, one is positive. In both instances, their product should be negative. Okay? So, again, I will repeat. If you're solving a less than inequality, the factors should have different signs. It cannot be that they have the same signs. Otherwise, you will be solving a greater than inequality. Let's illustrate these two theorems going back to the exercise that we had earlier. Suppose now that we have x squared minus 5x minus 6 greater than 0. And here I have here x squared minus 5x minus 6 less than 0. Again, as I was saying, if you know the solution set to this, then this solution set can already be derived from whatever is the complement of the one you arrived at here. Okay, let's find out. What are the factors here? This will be x minus 6, x plus 1, and then this is greater than 0. Same thing here, x minus 6, x plus 1, but that one is less than 0. In the theorem, this is my P, this is my Q. Or you can interchange. This may be your Q, this may be your P. But the thing is, the theorem is trying to tell us that if you are solving a greater than inequality, then there will always be two cases that you will have. We have case 1 here, will be x minus 6 greater than 0 and x plus 1 greater than 0. Or case 2, x minus 6 less than 0 and x plus 1 less than 0. Solving these two linear inequalities gives me x greater than 6 intersection x greater than negative 1. If you look at this direction of the inequality x greater than 6 and x greater than negative 1, both of them are moving to the right and the intersection will be starting from 6. So that is my solution for case 1. For case 2, we have x less than 6 intersection x less than negative 1. And both of the inequalities are moving to the left and their intersection will be this. Hence, my solution set will be case 1 union case 2. I will have here x greater than 6 or x less than negative 1. In interval form, we'll start from this, let's say negative infinity to negative 1 union 6 to positive infinity. Now, if the solution to x squared minus 5x minus 6 greater than 0 is this, then I can now read my solution to this inequality to be the interval that's not included here. That interval is actually from negative 1 to 6. Let's find out whether we can get this solution. Okay, applying this theorem, we are solving a less than inequality, so the two cases should be one factor greater than 0 and the other factor less than 0. So, writing case 1 here, what do I get? X minus 6 greater than 0 and x plus 1 less than 0. Or case 2, x minus 6 less than 0 and x plus 1 greater than 0. Solving for x here, I get x greater than 6 intersection x less than negative 1. Here, x less than 6 intersection x greater than negative 1. Let me show you the graph of this solution. I have here a negative 1 and this one is a 6. X greater than 6 means you're moving to your right. X less than negative 1 means you're moving to your left. And we're getting the intersection of these two graphs. Obviously, they don't intersect at all. So your solution to the case 1 is null set. Okay, let's take this solution here. We have a negative 1 here and a 6 here. X less than 6 means going to the left. And x greater than negative 1 means going to the right. And the intersection will be this interval. Hence, your solution here is from negative 1 to 6. And the solution set will be case 1 union case 2 or null set union negative 1, 6. I will get here from negative 1 to 6, which shows us that the solution is this negative 1 and 6. So there you have it, the use of the two theorems. Make sure that when you use the two theorems, your quadratic expression should be expressed in factored form. Now, it is indicating to us again that using the two theorems will be very convenient if we can factor the quadratic expression. Okay, so again, if p times q is greater than 0, you're solving a greater than inequality. These are the cases. You have to mention these two cases. And if p times q is less than 0, these are the two cases. And then your solution will just be the union of case 1 or case 2. Case 1 or case 2 is not case 1 and case 2. It should be case 1 or case 2 to indicate it's a union. So we are done with solution by using the two theorems. In the next session, we will be discussing another method. Have a good day!